A geometric version of the proof that a geometric series converges when r is less than 1. Take the line y equals x and the line y equals rx plus a. They intersect where x is a equals 1 over r, but then that horizontal length is a. That horizontal and vertical length of both a r, because the bottom line is at 45 degrees, ar squared, ar cubed. Notice that all of the horizontal segments correspond to the terms of our geometric series. All the way out to infinity. And thus, we bring all of those horizontal segments down, we see their total length is a over 1 minus r. So I can't actually do this entire thing without ever appealing to infinity and simply doing it in geometric terms. But this is a calculus course, not a geometry course. So let's do more relations to calculus. When I have a geometric or telescoping series, I could find an exact value for this sum. And all I did was I found the expression for the partial sum, and then I took the limit of that. And in both of these cases, geometric series and telescoping, finding the partial sum was the key. This is unusual. Often it is hard to find the expression for Sn. And so one of the questions I have, rather than just what's the answer, is does this series converge at all? Before I even try to find the answer, let me see if it converges. So what I need instead of a formula for Sn is I need a test. Does this diverge or converge? We have one so far. And right now, that's the only test I have. I either need to recognize, oh, this is geometric, then I know what to do. This is telescoping, then I know what to do. Or I have to see, hey, these terms don't keep getting smaller in the right way. So I would like to try and figure out a better way to simply know, hey, does this converge, does this diverge? My first thought, it would be nice to know whether or not this converges or diverges before I even bother to try and figure out what its total is. So I'm going to draw a picture. And I'm going to think of this like it was a Riemann sum. The first term in my series, 1 over 1 squared is 1. 1 over 2 squared is 1/4. 1 over 3 squared is 1/9. 1 over 4 squared is 1/16. And so on. Isn't it? So I'm going to draw boxes. And the first box I'm going to draw has a height of 1 and a width of 1. There. That's my first term. That's A1. My second box will go from 1 to 2 and have a height of 1/4. My third will have a height of 1/9. My fourth, a height of 1/16, and so on. Right? Isn't it? So far, so good? Would you agree that whatever this total is, it's the same as the area of all of those blocks going off to infinity? Consider those points. The upper right corner of each box. And let's draw a curve that connects them. Oh, wait a minute. At 1, that's got a height of 1. At 2, that's got a height of 1/4. At 3, that's got a height of 1/9. 4, a height of 1/16. That should be the function whose y value is the same as my series term. So far, so good? From 1 over to the right, I know that all of the area of all of those boxes is less than the area under the curve. So if I want to calculate that, remember my first goal before I figure it out is to figure out whether it converges or diverges first. I'm going to break it up. And I'm going to say this is really the first term, and then all the rest of them. But that second sum is the area of all of these boxes. And we know that that is less than the area under the curve. And all of a sudden, I hear an alarm go off in the back of my head. I've seen that before.
That means you integrate that. Whatever infinity would be like 0 minus.
Hold that thought. I can integrate that. That's an improper integral. If I integrate an integral involving infinity, I've got to turn it into a limit, right? But this is 1 over x to a power. Even before I do that integral, which I do want to do, even before I do that integral, you can tell me in advance, does that integral converge or diverge? And not only do I want to know if that integral converges or diverges, but I have a rule to help me about that. Because I think of this as one of those 1 over x to a power integrals. Does it converge or diverge? Chapter 7, section 7 or 8, I don't remember which one. Leo?
It's a P series.
It's not a series, it's an integral. I'm in the section on series, but I'm using a reference back from chapter 7. As an integral, does this converge or diverge? Why? Yes, but that isn't the only reason. We actually did the integral and we came up with a rule. Go find it. Careful. Yeah. I'd actually like to go to 7-8 because I don't want to approximate. I want to get an exact answer as to whether this converges or diverges. It's involving infinity, and 7-8 was the section involving improper integrals. And on page 531, I see at the top of the page a general statement. Any integral going from 1 to infinity, or more generally from a to infinity, of 1 over x to a power converges if that power is strictly bigger than 1, and diverges if that power is less than or equal to 1. This one, therefore, converges. Now, if we actually want to do the integral, we take the antiderivative, we put in the limit as t goes to infinity from the top, and we put in 1 at the bottom, and 1 over infinity goes to 0, and I do get a value of 1. So I know that this turns out to be 1. But wait a minute, what does that tell me about this? All I have to do is replace what's in this box with the 1. Now I know that series is bounded. Why is that enough? Tell me that this converges. I gotta go back to Thursday. Not bouncing back and forth is true, but I know that's true because this is always a positive number. So I'm adding positive numbers. Wait a minute, I'm adding positive numbers, right? That means we're monotone. We're always getting bigger as we add more and more things, and we have an upper limit. If we have a bounded increasing sequence, we must have a limit. Now here's the fun part. I have no idea what it converges to. But the total, whatever it is, should be less than or equal to 2. It could be a lot less than 2. I don't know. But I do know that it's a set of positive numbers being added. I'm going to get something that's a total. With a little bit of work from stuff we're going to see next semester, it is possible to show that the answer is pi squared over 6. Somebody give me a decimal. What's the value of pi squared over 6?
1.6449.
1.6449. That's a lot less than 2, isn't it? That doesn't matter. I knew that it was convergent. An upper bound had to converge somewhere under there. Huh. Questions? Well, because we're looking at sequences of positive numbers here, it is technically bounded below as well by 0, because you're never going to get anything negative. So it is technically bounded both above and below, but if I know I'm going up and I'm bounded above, that's enough. Just like if I knew I was going down and I was bounded below. It's only if I start wiggling all around that I have problems. That's later. Yes, sir.
How do you that they would do like the less than or equal to there?
Ah,
What that should include?
here,
For the bottom.
here.
Yeah.
Well, because I looked at this picture and I said that the area in the boxes is smaller than the area in the curve. So I cheated and I drew this first. This? Ah, well, because that is what we've got up here. This is this first box plus all of these other boxes, right? But all of those other boxes are smaller than the area under the curve. So there's where my less than or equal to comes from. But I have this result about these sorts of integrals, right? I should be able to take that result and translate it directly into this result about series. Let's consider this one instead. If I were doing an integral, I would say, oh, the integral from 1 to infinity of this thing diverges. Same rule, I have another integral of the form 1 over x to the p. But this time the p is smaller than 1. And so this one diverges. As a sum, though, how can I tie this integral back to the sum? Go the same picture. Only this time, I'm going to put my box for 1 here. Because again, this sum starts 1 plus 1 over the square root of 2, 1 over the square root of 3, 1 over the square root of 4, and so on. So the first number is 1. That's A1. The second number is 1 over the square root of 2, which is 0.7-ish. 1 over the square root of 3, 1 over the square root of 4, well, that's 1/2. So here's A3, here's A4. Now, this time, when I draw the picture, instead of using the left corner, sorry, the right corner, I'm going to use the left corner. Point, 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 point. Yes? This time, what is that function? Yeah?
The f(x) is 1 over 3x.
And now, Jack, how do these two compare? If I compare this sum with this integral, where's the inequality go? But what do we know about that integral? Which means that blows up to infinity. So what happens to this? The same thing. I don't even need to try and find the total. I know in advance it doesn't work. I haven't even tried to find the total. I'm not going to. That diverges. Nora. Yes. But I think I'm going to make it even easier on you. I can do this regardless of drawing the picture. Whether I draw the picture with the right dot or the left dot is less important. What I know happens to the integral. Which means I got to go back to those techniques in chapter 7 and use those to do integrals involving infinity. So let's suppose I have a function. It's continuous, positive only. Remember, I was looking at sums where all the numbers were positive. it's decreasing, and the nth value matches our sum. Then the sum, n goes from 1 to infinity, of an converges if and only if the integral from 1 to infinity of f of x dx converges. In other words, either both converge or both diverge. This, I hope surprises no one, doesn't tell me what the actual value is. It just tests whether or not it converges. So we're going to call this the integral test. Now, I wrote 1 to infinity. It doesn't have to start at 1. It could start anywhere. But the most common version of this theorem is written to start at 1. Why? Because of the integrals we did back in chapter 7 that went from 1 to infinity. That result on page 531 gives me a really nice statement. What I now have is a guarantee. If my series looks like 1 over x to a power, I can do that. We call these p integrals. I'm going to call these p series. Notice that one of the p series, when p is equal to 1, that's my harmonic series. 1 plus 1/2 plus 1/3. So here's another way for me to know that that series diverges. If my series starts somewhere other than 1, I want my integral to start somewhere other than 1. So if I had a series like this, look, I just filled you. You shouldn't be messing with me. Let's say I had this series. Notice it starts at 4. Well, then the integral I would want to work with should be the integral from 4 to infinity of 1 over x minus 3 squared dx, which I can show, using the techniques back in chapter 7, that that integral converges, which means this sum converges. Now this kind of makes me happy, because instead of doing a new idea, I can work back and say, I already know how to do all these integrals. Let's do integrals instead. Free to admit, integrals ain't easy. But it's better than trying to develop some brand new technique out of nowhere. Yes? Questions? This means automatically, though, I don't even have to do any sort of test. If I look at the sum n equals 1 to infinity of 1 over n cubed, I don't even have to test it. That converges. Similarly, n equals 1 to infinity, 1 over the 5th root of n diverges. Because I would read that as n to the 1/5. 1/5 is smaller than 1. Walk away. Not bad. Questions? Bleh. That's not a p-series. I don't like it anywhere near as much. P-series were much nicer. But
I'm thinking about the comparison test.
I'm glad you've read ahead, but we're not there yet. We have to use what we've got in our hands at the moment. I don't know what's compared to. I don't know what comparing is. We'll wait on that. Let's do this with the integral test. How can I do that with what we've got right now? I can look at this function. And now I can ask, is this continuous? Is this positive? Is this decreasing between 1 and infinity? Those are Calc 1 questions. So, is this function continuous? Why? It's differentiable. Well, let's look at the derivative then. So if you say it's differentiable, I better check. What's the derivative? Yeah. Yep. Derivative of the top, though, is 0. Over x squared plus 1, quantity squared is minus 2x over x squared plus 1 squared. Hey, wait a minute. The only place that is 0 or undefined is at 0, outside of where I care about. I only care about from 1 on. So that's continuous and differentiable. Positive. As a matter of fact, my derivative is negative everywhere, right? The function itself, though, that's positive. You're squaring something, you're adding 1, you're dividing 1. Okay, that's always going to be a positive number. What does this being negative tell me? Where? Everywhere except 0, right? To the right, and it's increasing on the left, but I don't care about the left. It's definitely continuous, positive, and decreasing on the interval from 1 off to the right. In some cases, it's more places than that. But all I care about is on that section. Last thing to ask, is f of n equal to an, I put an n in here, I get exactly that. That's how I got the function in the first place, right? Which means the integral test applies. All four of my conditions have been met. I can use the integral test. But now, I need to do that integral. I'm going to cheat. Turn back to your notes, chapter 7, section 8. We did this one in class back then. You did this integral already. But even if you hadn't, you should remember how to do the integral test. That means remembering how to do this integral. Sorry. You should be using the integral test, which means you need to remember how to do this integral. That is the limit as t goes to infinity, integral from 1 to t, 1 over x squared plus 1 dx. What's the antiderivative? Y'all got a formula sheet for a reason.
The inverse tangent of t.
It would be. So I get the inverse tangent of t minus the inverse tangent of 1 as t goes off to infinity. And now I need to remember what the inverse tangent graph looks like. This is where we do the math dance, the graph of tangent. So I have to go reflect through y equals x. The vertical asymptote becomes a horizontal asymptote. Where's this vertical asymptote on tangent?
It'd be a pi over 2.
Which means that's my horizontal asymptote. And that's my limit as t goes off to infinity. Wait a minute, what's tangent inverse of 1? What's the angle whose tangent is 1?
45 degrees.
I need it in radians.
Pi over 4.
Exactly. Wait a minute, that is a finite number. This converges. So, this total converges as well. The value of pi over 4 is like 0.78 something or other, right? It's less than 1. But I don't know whether the boxes are under or above, do I? I didn't draw the boxes. I didn't draw the picture. Oh, crap, Nora, how do I know whether this is below the number? It's bounded, but I don't know if it's under that number or not. This is a problem. I know that this converges. I don't know what it converges to. So grab your calculators for a moment. And let's add up just the first 4 of these. That would be the partial sum S4, 1 over 1 squared plus 1, 1 over 2 squared plus 1, 1 over 3 squared plus 1, 1 over 4 squared plus 1. So that's 1 over 2 plus 1 over 5 plus 1 over 10 plus 1 over 7. Wait a second. 1/2 plus 1/5 plus 1/10 is already 0.8. What is the approximate value of this as a decimal?
Would be like 0.85.
That's good enough. Which is bigger than pi over 4. That's okay. I don't know what this actually converges to by the integral test. The integral test only tells me that it converges. Doesn't give me the value. But in the long run, way off to the right, as I add up all of these different boxes, I could say, I don't know whether it's going to be under or over, but I know it's going to be close, depending on whether I put my boxes on the left or the right. If I put the boxes on the left, I'm really starting at n. If I put the boxes on the right, I'm starting at n plus 1. I've moved over 1 unit. So it's somewhere between these two, isn't it? But those are tails. They're only from some point on in a curve that's getting smaller and smaller and smaller. And in statistics, we call those the tails of a distribution. So I think of the main body of all of the data, and then I have these long little wispy edges. So this is the tail of my series. If I start at some point and move forward, I know that the integral is a little bit bigger than that. If I start one more down, the integral is a little bit smaller than that. Oh, so I have a boundary for the integral itself. Now this term in the middle here, that's the value of all of those boxes in the tail. We call that Rn, the remainder of n on. So, what if I wanted to know a closer estimate? I mean, 0.85, that's not that bad, right? But I only added up 4 of them. What if I add up more? I know. On my calculator, there is a way to do a sum. Under the math button, we did integrals in here, right? But only definite integrals. I can do sums, but I can only do finite sums. So I'm going to hit that summation button. And it gives me exactly the right picture. Now you can put any letter you want for the index. By default, I've been using n, but you don't have to use n. You can use any number. So I'm going to use, I don't know, how about we use j, alpha j. And j is going to start at 1. And instead of adding up the first 4, I'm going to add up the first 10. Of what? 1 over, parentheses, j squared plus 1, close parentheses. That's exactly what we were just looking at as a sum, wasn't it? Only now I'm adding up the first 10. I get a number that's 0.98, much closer to 1 than I originally thought. How close is that to the right answer? I don't know. But I can use this to find out. The remainder from 10 on is less than the integral from 10 on. The integral of what from 10 on? The integral of 1 over x squared plus 1 dx. But I know how to do that integral. We just did it to check that it converged. I know that this is limit t goes to infinity, integral from 10 to t, 1 over x squared plus 1 dx, which is the inverse tangent, minus tangent inverse of 10 this time, not 1. But I know this number is pi over 2 minus whatever the inverse tangent of 10 is. So I grab my calculator and you give me a decimal. And I can compute pi over 2 minus the inverse tangent of 10, and I get 0.099, let's call it 0.01. In other words, after 10 terms, I'm within 1% of the right answer. Sorry? Oh, you're right, it would be 0.1. I rounded the wrong way. I'm within 0.1 of the right answer. Wait a minute, 0.98 is within 0.1 of the right answer, so the answer is not bigger than 1.08. What if I wanted to be within 0.01? I'd need to know what value here made this integral less than 0.01, right? And I can use my calculator to solve for n. So I can do this graphically. Tangent inverse of x, pi over 2 minus 0.01 I'm going to have to zoom that in on the y-axis to see these two apart. So let's make this go from 0 to 2. I apparently have to go further to the right, yes? Because they're not crossing yet. So I have to go way out here, much bigger values of x. There's the inverse tangent. All I have to know is where those intersect. And I can find that by calculating the intersection. They intersect out at 100. So if you want an answer that is off by less than 0.01, you can now do that by doing this sum and going to 100. There's your answer. Accurate to within 0.01. You tell me how accurate you need to be. I'll tell you what n you need to go to. An epsilon and an n. You tell me how close you want to get. I'll tell you how far out you have to be. There are lots more tests. We'll do comparisons. But I need to understand that comparisons only work sometimes. And that is what we'll look at on Wednesday. I will see you all then. Have a wonderful rest of your day.